Alright, our last example here, we have our cherry flavored snow cone. And it's leaking from its paper cone. Those things are terrible and they always leak, alright? So, actually, maybe I should make it red. It's starting to drip out, right? Probably making a mess all over. So, it's starting to drip out and at a rate of 2 cubic inches per minute. So, we could say that the volume is decreasing at a rate of 2 inches per minute. The paper cone's top radius is 2 inches, and it's 5 inches tall. Alright, so I'm just going to sketch my picture over here. Oh, that's a 2, isn't it? Okay, so try again. Top radius is 2. That looks like a 2, right? Sure. 5 inches tall. When the depth of the cherry rasp mixture is 3 inches. Okay, so that's what we're talking about at this point. So when my height equals 3 inches, that's that snapshot moment. Alright, the important moment when you need to realize what's going on here. How fast? So for part A, find dr dt. How fast is the radius changing? Alright, so we have r there. For my equation, alright, I could write, I could say like 2 over r equals 5 over 3. Maybe not 3. Let me double check here. Actually, it wouldn't be 3, right? It would be h because we don't know what the height is. We're just saying h right now. Alright, for the height. Another way of writing that, if you guys remember from geometry, you could say 2 over 5 equals r over h. Or 2/5 h equals r. Or you could say h equals 5/2 r. Either of those would be fine. Alright, so we don't know which one we're going to use, so I just let them all out there. So we're talking about the volume changing. So it's 1/3 pi r squared h. Alright, instead of using r and h, I'm going to go ahead and use one of these forms I have down here. Alright, so I'm going to replace my h with my 5/2 r. So I have r squared, 5/2 r. Alright, so actually I should change that 5 pi over 6 r cubed if I multiply that out. So if I take the derivative now, okay, so we get what? 5/2 pi r squared dr dt. Alright, plug in the values that I have, so when h, should I say when h equals 3, but that's not really helpful, right? So plug in if h equals 2/5 h equals r, 2/5 times 3. We could say when r equals 6/5. Alright. Actually, we know what dv dt is. Let me clear that out. So dv dt, which is -2, equals 5/2 pi r squared dr dt. Okay, then we have -2 equals, start to simplify this, 5/2 pi times 36 over 25. I could reduce some of that. Alright, so that would be 5. So we have 35 over 10. Right, but then we have -2. Not 35, 36. Alright, I can't read this. That's fine. So actually, I could simplify even more. We get 1 and 18. Alright, -2 times 5 over 18 pi. Still have that pi there. So -10 over 18 pi, which can still be reduced to -5 over 9 pi inches per minute. So that's dr dt. So the radius at that point is decreasing at a rate of 5 over 9 pi inches per minute. All right, so this next question is about understanding how fast is it leaking out? Well, if how fast is it leaking onto somebody else's clothes? All right, so we have a shirt here. Well, it's leaking out at a rate of 2 inches per minute. So part B, it's the same thing, but it's positive. It'd be 2 inches per minute that it's leaking onto the shirt. Part C is going to take a little bit more. All right, so let's clear this picture out. We have this cup that it's leaking into, okay? Small cylindrical cup, so we have this cup. And now it's starting to leak into, to fill up. A 2-inch diameter, so our radius is 1. And how fast is the height changing? So we're trying to find dH dt. All right. So we have this dV dt. The volume is increasing at a rate of 2 inches per minute. And the volume, I'm going to use V, and again, even though it's not the same volume, okay, that's why I'm writing it in green. All right, so volume of this is going to be pi r squared times height, but my r is just 1, so the volume equals, and the volume's not changed, I mean the radius isn't changing at all, it's a cylindrical cup this time. All right, so now dV dt would equal pi times dH dt. 2 over pi inches cubed per minute would end up being dH dt in my case. All right, so that's not too bad of a problem, and we have a couple different shapes, a couple different variables here. And this one is one that I see that a lot of people make mistakes with, even though it's not too tough. It's just the idea behind it, how to set it up. Once you know how to set these up, they're all very similar, and you should be able to figure it out. All right, so street lamp. That's a beautiful street lamp, right? And a 5-foot tall boy. So we're going to make this a triangle because we have some shadows along the ground here. All right, the street lamp is 30 feet. The boy is 5 feet tall. I'll call this X. All right, and I'm going to call it Y. I could use S for shadow, but my S's turn into 5, so I'm not going to do that. Now the boy is running towards the street lamp. And he's running at a rate, so dx dt, he's getting closer, so it's decreasing. That distance is decreasing. -6 feet per second. And we're talking about the snapshot moment when x is 4. Okay, so we have our snapshot moment. Let's look at our equations. What different equations do we have here? Well, we could use similar triangles. Again, this is a geometry concept. 30 over x plus y equals 5 over y. And there's a couple of ways to write this here. We could say that 30y equals 5 times x plus y. Oh, come on, you pen. I could say 6y equals x plus y, or 5y equals x. All right, or y equals 1/5 x. I don't know which one I'm going to need yet, so I'm just laying it all out there. All right, so for part A, how fast is the length of his shadow changing? Now, y is my shadow, so I'm trying to find dy dt. Okay, so I can do that by analyzing the shadow. I have this equation, the shadow length is equal to 1/5 times x. So dy dt, the change in the length of the shadow, would be 1/5 dx dt. Alright, plug in what we have for dx dt. 1/5 times -6. So the length of the shadow is decreasing at a rate of 6/5, okay, or 1 1/5 feet per second. Now, how fast is the tip of the shadow moving? All right, this one is where people have a little bit of trouble. But what we're looking for here is the derivative with respect to time of the sum of x plus y. So we're looking at this whole length here. How is that changing? All right, that is the same exact thing of doing dx over dt plus dy over dt. It's just like the distributive property. All right, so at that specific moment, when x equals 4, the derivative of x plus y with respect to t would be equal to -6 minus 6/5, which would be -36/5 feet per second. All right, so that finishes up all of our examples here. If you go back and look at kind of the process, what we're doing. So pictures help, okay? You have this whole list of things to do, but just to go back, pictures are very important, okay? Getting equations in one variable, also very helpful. All right, labeling. Labeling is vitally important. What's your sign? What's changing? Writing your equations. All right, all of these things you need to do every single time. If you ever get stuck, you have this page in your notes, 11 easy steps to solve these. Look, picture, that's what I just talked about. Labeling, all right, identify the rate you're trying to find. Do as much as you can in the beginning, all right, and it'll make everything else easier. So keep working on your problems. I know you can do it. Don't give up. And the last step, make sure you smile when you finally do accomplish something. You guys are getting better at these. Okay, so take your time to show yourself that. Have a great day.